In the previous episode, we took a closer look at what exactly a program is and what kind of instructions we are likely going to see. We determined that for our processor to be able to run programs, it needs a register to store the program counter, which is the current position or address in the program. It also has to be able to advance the program counter to the address of the next instruction. And to implement control flow, the processor needs to be able to perform relative jumps, say 3 instructions forward or 5 instructions backwards, and absolute jumps, say go to address hex 108. We also want to disable the program counter at times, for example, when an instruction has to wait for some earlier computation to complete or some data to arrive. And we want to be able to reset the processor such that it begins executing the program from the top. Be sure to like and subscribe if you want to see how we implement this and want to see the project unfold. Last time, we started out by using a 74HC377 register chip to store the current program address, and we verified that it works as intended. That did let us tick off the program counter register on our wish list, and thanks to the enable signal that is already included in the 377 chip, we could also tick that off immediately. So as a next step, we would like to be able to compute the address of the next instruction in the program. What this usually means is that we have our program counter here, and we want to add a fixed offset, like 1 byte if our instructions are a single byte, or 2 bytes if our instructions are 2 bytes. Or maybe we have differently sized instructions, and then we'll add whatever byte number is needed to step over to the next instruction. To do this, we'll use a 74HC283 chip. The 283 is a 4-bit binary full adder, which means it can add 2 4-bit numbers. And it will produce a 4-bit result again. It also has this carry in and carry out lines, which allows you to chain multiple of these chips together to produce adders of a larger bit width, which is what we're going to use here as well. First, let me program a bit pattern, which is a bit more obvious to see what's going on with the adder. So our goal now is to add a constant offset to this value and see if we can store that back into the program counter again to basically make it step through a program. Let's start by hooking up one of those and see if we can get things to work. Let's connect power and ground immediately. And since this is the first adder, there's no carry signal of a previous chip that we can feed in. So let's tie the carry input to 0. As one of the inputs to the addition, we're going to bring down the current state of the program counter. Bit 0, bit 1, bit 2, and bit 3. The other input to the addition is the number of bytes we want to step ahead in the program. So let's tie this to a 1 at the moment, so we always keep adding a single byte. First bit is a 1, and the other bits are 0. To to see what's actually happening with this chip here, let me hook up one of these bar graph LEDs again so we can visualize the result. Let's move this all the way out of the way here. And let me wire up the output of this to the LEDs. First bit of output. Second bit of output. Third bit of the output. And the fourth bit of the output. This is a bit of a stretch. It just barely works. There's also the carry output on this adder, which we can bring out to an LED so we can observe what's going on there. All right, let's see if the setup works. I just realized that I've mixed up these two wires here. So what's going on here is that this is a 4-bit adder. So basically we're just taking the lower 4 bits of the PC and doing our work there. We're bringing down the 4 bits as one of the inputs to the adder. And then as the other input to the adder, we have a constant 1 here, which is basically the first bit set to the high voltage, and then all the other bits are set to the low voltage. And then this adder is doing the addition, doing its magic, and it's producing another 4-bit result plus a carry flag, which is not set at the moment. And we'll bring it over here and we can see what's going on. So if we just look at the lower 4 bits here, this is a 5. And after we're feeding it through the adder, which adds a 1, what we're getting out is actually a 6. And we can also play with the step sizes. Currently we're just adding 1, but we might as well just add a 0, which gives us the same output as we had as an input. Or we can actually add more than 1. So let's say we tie the second bit to high, which is going to be the value 2. And this 5 we had at the input has now become a 7. Or we can add 4. And we can basically play around with this however we like. Let's also check if the carry flag is working. For this, we need to add 2 numbers together which don't fit into 4 bits anymore. So a common case would be that this is at the maximum value, so all 1s, which is a 15. And we're trying to add 1, which is a 16, which doesn't fit into 4 bits anymore. So let's try to provoke that. So we're adding a 1 again, but now let's program in a 15 here. And let's clock the program counter. There you go, that's a 15 now. The carry flag output has gone high, and the result is 0, which 16 in binary is the 5th bit is set and all the lower 4 bits are just cleared. So that makes perfect sense. So let's extend this now to add the second adder. So we have a full 8-bit addition going on, not just the 4 bits, and we can add whatever we want to the program counter. So we can use the full 8-bit range of values. Move this out of the way a bit. Let's wire up power and ground again. All right, since this is the second chip in our adder chain, we can bring this carry output of the previous chip over to the carry input of the next one. We don't need the LED anymore. Now in practice, the number of bytes we're going to add to the program counter just to step to the next instruction is going to be fairly low. It's going to be 1 byte, maybe 2 bytes, or if we're super fancy and we can, for example, execute 2 16-bit instructions in parallel, it will be 4 bytes. So only the lowest few bits of input we're actually going to use. In this upper case, we'll just wire one side of the addition to all zeros. Bit 0, bit 1, bit 2, and bit 3. Next, let's bring down bits 4, 5, 6, and 7 of the program counter to the other side of the input here. That's bit 4. Bit 5. Bit 6. Bit 7. Now let's bring the outputs to the upper 4 bits of our result over here. Great. Now let's see if this works. We have our 15 in the lower 4 bits and the upper 4 bits are just a value. We're adding a 1, which causes the lower 4 bits to overflow to 0, and the 5th bit here becomes a 1. So that seems to be working. Now that we're able to add basically a byte offset to the PC and we get in essence a new PC value out here, what we can do is we can hook up the inputs to the PC register to this output down here, which will cause it to basically assume this value on every clock cycle, and we can basically create a loop and step through individual values of the program counter. So let's try this out. So this is now taking the value displayed here and it's bringing it over to the input of the register. So on every clock edge, we should basically step to the next instruction now. Let's give this a try. And as you can see, the PC updates. We have a current value. We're adding a 1 through the adder circuit here. We're getting a new value. And then as soon as I hit the clock, that value gets stored over here. We're already preparing the next value. And we can change the step size. This is now wired to a constant 1 at the moment, but we can wire it to a constant 2, for example. And if we step, we can basically see that the lowest bit remains where it is. It's a constant 1 because we're always adding a 2, so this isn't affected. And we're stepping through the program in increments of 2. And we can even let this run on the regular clock. Now, to prevent things from becoming too messy, let me actually bring down the current state of the PC from here down to the other board, where it's going to be easier to access. Let's see if that still works. Perfect. Now, an interesting thing about the arrangement of the step size we have here is that we can basically connect all the inputs to 0. So we have a step size of 0, which would basically make the next PC state be exactly the same as the current one. So the PC basically stops counting. It just stays where it is. But we have the clock enable signal here of the flip-flop to do that. So we're actually never going to use that step size of 0. Now remember that this adder chip had a carry input, but we tied it low because we weren't using it. But what we can do is we can actually use that carry input and tie it to high to always add at least 1 to the current PC state. And the other wires we have over here, then basically the lowest 2 bits we can use to increase the step size from 1 to 2, 3, or 4 by choosing the correct value. And the upper 2 bits basically become unused because we never want to do more than like a 4-byte step. So we can tie these to ground. So let me do that. First, the carry input goes to high. And the upper 2 bits of the input, which are on the other side of the chip here, these we can constantly pull low because we're never going to use them. So now if we select a 0 for the step size, we should be doing single byte steps. Let's see if that works. That seems to be working. If we choose a 1, we should actually be doing 2-byte steps, which is working. And then selecting a 2 will actually give us 3-byte steps. And selecting a 3 will give us 4-byte steps. Perfect. That's working, and this makes wiring up the step size much easier. Now, one thing that's kind of scary is that the wiring here is already messy, and we're only doing like an 8-bit add over here to the PC counter. So let me actually replace these wires that bring the current PC state over to the adder inputs with some properly cut wires that are closer to the surface of the breadboards. That's the lower half of the wires done, so let's move up to the upper ones. All right, let's see if this still works. Let's pick a more reasonable step size again, step size of 1, by wiring this thing up to 0 down here. Looks like we're still good. Now, in terms of what this adder actually computes, this is basically the address of the next instruction in the program stream if we just kept stepping through the instructions without doing any branches or jumping around. And that's going to be pretty useful in other places of the CPU. So we'll want to have this value accessible pretty easily, so we can hook up a big cable here and get that value out. So what I want to do is actually these cables here that basically bring the next value over to this LED over here. I want to have them over on the right side where we can easily plug in a DuPont cable to basically grab them off the board. So let me do that. That's the bottom half done. Let's move up to the upper half. All right, so what we should be able to do now is that now that we have a proper next instruction address over here, we should be able to rewire this input to the register and basically take the next state right from down here instead of over here at the LEDs. Let's see if this still works with this new wiring here. The LED is still working, but that's using the old cabling. So let's see if this actually moves into the PC register through this wire. That looks great. So looking back at our wish list, we've added the capability for our program counter to step forward to subsequent instructions. And not only can it step by single byte increments, but also by 2, 3, and 4 bytes at a time. In the next episode, we are going to look at relative jumps, which are going to be very similar to the stepwise incrementing we implemented in this episode. Thanks a lot for watching. Like and subscribe if you'd like to see more of this, and see you next time.